Hello everybody, welcome to part 7 of the linear and nonlinear relationships topic. Today we're going to be moving on to hyperbolas. So what exactly is a hyperbola and what does it look like? Let's find out. We're going to start with the equation y equals 1 over x. So we're introducing a fraction into our equation. Before we get started by graphing some points, have a think about what happens when we change the denominator of a fraction. What happens when this number gets really big? What happens to the whole function? Or when this is a really small number, what happens to the whole function? Alrighty, let's go ahead and create a table of values. Let's start off with a nice easy one like usual. X equals 1. When we substitute x equals 1, we get 1 divided by 1, and so that's just 1. Now let's increase our values of x. When we substitute in x equals 2, we get y equals 1/2. And when we substitute in x equals 3, we get 1/3. Likewise for 4, we get 1/4. And let's skip a few. Let's say we went to 100. 1 over 100 is 1/100th. So we can see that as we increase our values of x, our y values get smaller. But not negative, just smaller positive values. Let's keep positive x values now and work our way towards 0. So let's start off with 1/2. If x is 1/2 and we substitute 1/2 in here, we're now asking ourselves, what is 1 divided by 1/2? Or how many halves are in a whole? There are 2. How many thirds are in a whole? 3. How many quarters are in a whole? 4. And we could do the same thing as before. Let's skip a bit and go to 1/100th. 1 divided by 100th is 100. So as we get smaller and smaller positive values of x, our function gets really, really big. So let's graph this part of the function. Let's start with x equals 1, y equals 1. So this point here, and we'll draw that here. Now going in the positive direction, at x equals 2, y equals 1/2. At x equals 3, y equals 1/3. And at x equals 4, y equals 1/4. We won't worry about drawing the point 100/100th. Let's start with the point 1/1. As x gets bigger, y gets smaller. So our next point is 2 1/2, then 3 1/3, and 4 1/4, getting very close to the axes. Going the other way, at x equals 1/2, y equals 2. At x equals 1/3, y equals 3. And at x equals 1/4, let's start with the point 1/1, right here. As x gets bigger, y gets smaller. We have the point 2 1/2, 3 1/3, and 4 1/4. So I can see getting very close to the x-axis. What about these smaller values of x? At x equals 1/2, we got y equals 2. At x equals 1/3, we got y equals 3. And at x equals 1/4, we got y equals 4. Let's connect those points. In previous graphs, we've talked about asymptotes. That is, a line that the graph will never quite touch. It will always go closer to it, but it will never touch. With a hyperbola, it appears we have two asymptotes. As x increases in value, the curve will get closer and closer to the x-axis, but never touch it. And the same appears to be happening vertically. But let's just check an important point. What does happen when we set x equal to 0? Is this allowed? Well, hopefully you're aware that it's not. We can't have 0 on the denominator of a fraction. So that's why we have a vertical asymptote along the y-axis, or along the line x equals 0. So you might ask, Mr. Laurie, in our table we only had positive values of x. Well, if we set negative values of x, we'll get very similar results, except all our y values will also be negative. This is what our curve would look like. We've already drawn this part of the graph. We would get a similar, well, exactly the same type of shape over in this quadrant. All our negative x values would give us negative y values. And so what we have is two distinct parts to this graph that are the mirror image of each other about this line, y equals minus x. Let's write a few key features of this graph. And instead of saying y equals 1 on x, we'll generalize it to y equals k on x. The first thing we noticed was that as x got really large, or approached infinity, y got really small, or approached 0. Likewise, as x got really small, or approached 0, y got really large. And we have a similar thing happening down in the negative quadrant. The next thing we notice is that the function does not actually exist at x equals 0. That means we have a vertical asymptote. The graph will get closer and closer to the y-axis, but it will never touch it. Finally, we notice that the graph has two distinct parts. The first part that we looked at is located in quadrant 1 of our number plane. Quadrant 1 is up here. The second part of our graph is located in quadrant 3. So quadrant 3 is down here. These are quadrants 2 and 4. Having our graph in quadrants 1 and 3 occurs when k is positive. When k is negative, we get something different, which we'll look at soon in Desmos. These parts of the graph are symmetrical. That green dotted line that we drew before, that's like the mirror. Okay, let's go and have a look at Desmos and see how our graph can change when we manipulate the variables. So here is our initial graph, y equals 1 on x. But remember, this 1 does not have to stay as a 1. It could be any number k. We could have y equals 2 on x, y equals 3 on x, etc. And we can see how the position of the graph changes. But let's have a look now at what happens if our value is negative. When our value is negative, we switch quadrants. Instead of being in quadrants 1 and 3, we're now in 2 and 4. So making the entire graph negative switches the quadrants. It's still symmetrical, except now it's symmetrical about this line, as opposed to our original graph, which is symmetrical about this line. Okay, let's start moving our graph around a little bit. From our work on previous nonlinear functions, if we add anything to our original graph, that results in moving it up and down. Let's say we add on 2. Our graph has now moved up 2 places, and the horizontal asymptote that was previously at y equals 0 is now at y equals 2. So our graph will never touch this line. It will get close, but it will never touch. So when we're graphing these hyperbolas, and we have to translate our graph or move it, it can often be good to move or draw our asymptote in first. If we subtracted 2, it would move our graph down 2, with a horizontal asymptote at -2. So that's moving it up and down. How might we move our graph side to side? That would involve moving the vertical asymptote. The vertical asymptote is currently at x equals 0, this blue line here. Remember how we got that? We don't want the denominator to be equal to 0. So if we wanted to move our vertical asymptote, say, to 2, we would need the denominator to not be able to equal 0. If x equaled 2, we would get 2 take away 2, which is 0, and we're not allowed to have that on the denominator of our fraction. So plussing or minusing within the denominator of the fraction will result in our graph moving left or right. If it was a plus 2, we would not be able to have the value x equals -2, because -2 plus 2 would give us 0 here. And we can see on the graph that this blue line, x equals -2, is the vertical asymptote of our hyperbola. So let's go back and summarize this with a few little sketches. The first change we looked at was if we changed the value of k so that it was now negative k on x. Remember, this changed our graph from being in quadrants 1 and 3 to being in quadrants 2 and 4. So our hyperbola was here and here. Let's go back to our standard hyperbola, y equals k on x, but let's add on some constant at the end. This resulted in shifting our hyperbola upwards. Instead of our asymptote being along the x-axis, we've now shifted it up by c places. So the asymptote is now the line y equals c. We still have the same vertical asymptote of x equals 0. So it would now look something like this. An important feature to note is that the hyperbola, in this case, would now have an x-intercept, which might be a useful point to show in a question. Finally, we moved our hyperbola side to side. We did that by modifying the denominator. When we have y equals k on x minus b, we have a new vertical asymptote at the point b. So if we've moved our vertical asymptote across, this is the line x equals b, because if we substitute b in here, we get b take away b, which is 0. So the graph doesn't exist. Now we can draw the rest of our graph, just like before. We have this section here, and we have this section here. Once again, we've created an intercept when we move our graph from side to side. In this case, we have a y-intercept. Okay, that's the end of our video on hyperbolas. I hope you've enjoyed. All the best with your questions.